All right, let's get started. So today we're going to start studying motion planning. So we have so far been studying a bunch of different topics, but we kind of started with state estimation, figuring out where the robot is in the world. Then we studied control and figuring out how to do feedback control so we can deal with disturbances. Right? And so the last few classes we covered feedback control, PID control, bang control, LQR, versions of LQR, and then NPC. Right? And all of these are basically saying, you know, path is given to you, how do you stabilize around that path? How do you follow that path without getting, you know, thrown off by disturbances? And today we're going to figure out how to find the paths, right? So in high dimensional spaces, like I was just talking to them about, we want to get somewhere. We want to figure out how to do it in a way that's safe and collision free. And so that's what we're going to talk about today. And so for the next maybe 4 lectures, we'll talk about planning and search, and then we'll talk about machines. Okay, some logistics before we get started. Homework 3 is due on Feb 14th. Let's try and keep the date kind of firm and not have too many extensions. If you think that there's an issue that's going to happen, let us know a little early, just so we don't overburden the TAs. And the paper commentaries will also be due. Then I will post them. The questions will be pretty much the same. Any other questions on logistics or anything else? Great. Okay, let's talk about motion planning. So today our structure is going to be, we're going to start by scoping the problem and try an overview of what motion planning is. Then we'll try to formalize the problem a little bit. We'll try to study why this problem is hard. And then we'll try to think about what some approaches might be to start solving the motion planning problem. Okay. So if we zoom back out to our design of a robotic system, we started from sensors, we want to go to actuators. We started by defining our knowledge of the world in our world model or simulator. And then we said, okay, the first thing we need to do is map from sensors to where we are in the world so we can use the world model. We covered techniques like Bayesian filtering to do that. And then we said, okay, there's this magical thing called planning that we haven't really talked about yet. But once the planning gives you a good path, like it gives you a path through the hills that you need to follow, then control lets you go and follow that path, and things like LQR, NPC, or PID control let you follow those paths, right? And all of those are just different ways to follow a planned path. Now, what we're going to talk about now is how do we actually decide if you have a long range problem, you want to get from here to, you know, LA in your helicopter, like how do you plan the right path, which you can then use for control. Right? So the difference between control and planning is a bit subtle, and we'll talk about that in a second. But at a high level, we know where we are in the world. We know, given a path, how to follow it locally. We just need to figure out what the path is. Right? And it's important to remember that planning a path is not just like in 2D space, it's in full space of the robot. So it's in position, orientation for a robot arm, it's in where all the joints will be, right? It's in the configuration of the robot, not just in 2D space. And so that's what makes it fun. Okay, so if we go back to our sense, plan, act paradigm, we have sensing, which estimates robot state. We have planning, which tries to plan a sequence of motions, and we talk about control to follow the path. And we've kind of covered these two over the last 5 weeks. And today we're going to think about how do we plan a sequence of motions so that when you put all of these pieces together, you can go from sensor to output. Right? Essentially, the way a system will work is you take in your sensor reading to estimate where you are, you run planning to figure out where you want to go, and then you run control to actually execute it in the world. So that's kind of where this fits into the picture. Okay. Okay, so let's try to think about this example of flying from Seattle to LA. And let's try to think about what planning means. I think planning is a bit of an abstract term, it's overloaded. So if I was to, you know, start planning to go from Seattle to LA, how would you start? Like, what's the first step? Yeah.
Straight line.
Straight line. Okay. Yeah. The straight line might be part of it, right? But I think you want to kind of think of the steps that you're going to take at the highest level, right? You want to say, I want to go to the airport, I want to get on my flight, I want to get off my flight, and I want to go to wherever I want to go. That's there's the highest level of planning, which is abstract. And then you want to take that highest level of planning and you want to make it a little more concrete. So it's like, I want a more concrete plan of saying, I want to get to the terminal. I want to board an airplane. But when I say get to the terminal, what does that mean? Probably means I have to call a cab. The cab is going to take some route. The route is going to get me there, right? And so whenever you do planning, it's like at a hierarchical level in most cases, where you have an abstract set of steps that you decide, right? And you kind of leave the details for later. And so you decide the highest level planning, leave the details for later. Then you pick one of those abstract things and then you try to concretize. And so you're saying, I want to get to the terminal, and I now zoom in on getting to the terminal and I plan how I would get to the terminal. So I'm gonna it's still abstract. It's still calling a cab and taking some route, etc. It's still not telling me how to do things concretely, but it's one level lower, right? And then you can take that, one level lower to things like, sorry, one more second. So you start at the highest level. We talked about getting to the terminal, boarding an airplane, etc. Highest level plan. The next set of things you talked about is, let's say, take any of the things like getting to the terminal, going to concretize it into like some smaller steps, and then finally, you want to like concretize that to the motion of getting out of your house, right? And so, any planning problem is like multiple levels of abstraction, and in this class, we're only going to study the lowest level of abstraction. So, in any practical planning system that you deploy, you will probably have some sort of discrete planner at the highest level. And then you would have some intermediate level planner, and then you would have a low level planner which decides the series of motions that help me get out of my house. And so in the literature, you'd often call the higher level things task plan and the lower level things motion. And so we're not going to study task planning a lot in this class, but there's a whole body of work on task planning, motion planning, and task and motion. Does that make sense? So a good rule of thumb for planning, I guess a planning problem is anything that tells you how to go from place A to place B under constraints. And a good rule of thumb for planning problems is having hierarchical abstraction, just so that you don't have a combinatorial explosion in the size of the plan. Right? Imagine that I had to like plan all of the motions to go from Seattle to LA. That's like a totally impractical thing. But if I can hierarchically abstract it, it becomes much more practical, right? So in general, for a robotic system, you want to do hierarchical planning. But in this class, we're going to really focus in on the low-level problem of if I want to get out of my house, right? How do I plan the series of motions to get there? Does that make sense as scoping? Okay. What are some challenges in this hierarchical scheme of doing things? Or is it always a good idea? Yeah. Yeah. Right. You might have constraints that make it hard. But that's kind of it might happen at the lowest level. I guess what often becomes tricky is when the levels interact. So for instance, if how I get out of my house really affects my higher level thing. Like for instance, there's no way I can get out of my house and take my car, then it affects my higher level plan. So when the like different levels interact, that's when it becomes tricky. So a lot of the research on task and motion planning is how do I like jointly plan over the different levels of abstraction without like solving the entire messy long horizon problem, just like accounting for the interaction between the levels. But we are going to specifically think about this last level of how do I get out of my house, which is a problem called motion planning. It's saying I want to get from one place to another with a physical system, and I want to do it while obeying the constraints of the world. So let's start to think a little bit about what makes motion planning difficult, right? So planning in AI history has been used for things like chess and these things are called 8 puzzles or whatever. Rubik's cubes and lots of other games, right? Things which have discrete action spaces, like clearly defined rules, discrete state spaces, right? And oftentimes you have like pretty great intuition on how to define the different pieces, how to define the preconditions and effects. And a lot of classic AI planning methods have just been essentially logic methods. They're like A implies B, B implies C, B implies E. If I want to get E, what steps do I take? Right? And so a lot of the tools that were used in the 80s and 90s and even early 2000s are basically classic AI planning methods, which are almost always discrete search methods. They're almost always discrete search methods, which are trying to say discrete state space, discrete action space, well-defined rules. How do I solve the problem? Yes. Now, what makes motion planning difficult is that in a robot, you don't have discrete state space, you don't have discrete action space, you don't have great intuition. In high dimension, all of your intuition breaks, and you don't exactly know the world everywhere. And so you have continuous state spaces. Action simulation is not trivial. You have uncertainty. You often have things that are not polynomial. You can't just like teleport through the air. The world has physical constraints, right? And so planning in these kinds of problems is a lot harder than planning for a Rubik's Cube or an 8 puzzle. And I'll try to do my best to convince you what. Okay. So, a canonical problem in motion planning is this thing called the piano movers problem. And the piano movers problem kind of looks like this. Basically, you have this crowded house, you have like furniture all over, right? And you're trying to like put a piano inside this house, and you can only slide the piano, and you want to get it somewhere without hitting anything. It'd be a little hard to see, but here you can see they're trying to get chairs in. But basically, they're trying to get chairs in, and now they're going to try and get a piano in. So you can think of like a setting where you have a bunch of obstacles which are fixed to the ground. And then you have a sliding piano, which you can, slide, translate, and rotate. You're trying to move this piano in through these obstacles so that it doesn't hit anything. Right. And so this is a classic motion planning problem because you have like a physical piano which occupies space. The obstacles are not point obstacles, so you can't just like teleport. It's not just a grid search problem. You have to account for the geometry of yourself and the obstacles. So you can see here the piano is right. So they're kind of like, for instance, you want to get up the stairs, you have to like back it up a certain way so that it fits, etc. So if any of you move furniture and you're like yelling pivot, 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 right? That's kind of a motion planning. And so I guess the piano moving problem is arguably the simplest motion planning problem, which has like non-trivial complexity. And so we'll talk about the complexity of these problems later, but you can almost think of a problem with a piano moving problem is something like you have an environment, right? You have like some sort of a piano, let's call it like some sort of something, right? And then you have like obstacles on the way. And this piano can rotate and translate. And you're trying to like see how to like maneuver so that it fits through things, it gets through obstacles, right? And there's like more and more fancy versions of this, but that's the fundamental problem. Now, like the nice thing about the piano movers problem is that it also exposes other complexities in your setup, right? So imagine that now instead of just like part of what makes this problem difficult is that you can only slide the piano, right? Now imagine you could make the piano fly, right? Now what you've done is you've increased the dimensionality of your system. And so the constraints are easier, but the dimensionality is higher, right? So there's often a trade-off in these motion planning problems. You can like increase the dimensionality, but then the problem becomes harder, right? Easier in certain ways, harder in other ways. So that's kind of, fundamental problem. But where this is actually useful is for things like humanoid robots or robots in the space station, things where you have to like plan motion through cluttered spaces without hitting anything and obeying constraints. So like for instance, for this robot on the space station, you have to have the constraint of holding onto a rail, and you have to move through a cluttered space in your space station, and you have to do it for like what a 30 degree of freedom robot, right? And that becomes tricky, especially under the like many constraints that you have to place. That's what makes these high dimensional problems hard. And for all these things like the DARPA Grand Challenge and everything you've seen, like all of them use motion planning somewhere in this. None of them are using neural networks to run things. All of them are using motion planning. Okay. So that's kind of some examples of motion planning. Here are some examples of like simple algorithms in action for things like robotic manipulation, right? You want to have a bimanual system doing something. Like you've seen a robotics lab, you have a bunch of bimanual systems in there. Manual systems get complicated with robot motion planning because you're trying to jointly plan both these things together, right? And you're trying to figure out how to move quickly through the space without hitting each other. So you can see that they're like trying to move past each other. And depending on the motion, like that's non-trivial, right? Because they interfere with each other and they interfere with themselves. Okay, so this is a general premise of motion planning. You're trying to like informally, you're trying to like move from one place to another without hitting anything while obeying the constraints of physics and obeying the constraints of your environment, right? So on the space station, for instance, you have constraints like you have to hold on to things, which are not just obstacles. So some of the constraints can be limited to obstacles, but you can have more constraints. Like hold on to something, or let's say you're like trying to transport, a glass of liquid from one place to another. You don't want to spill the liquid. That's an addition. Okay, so some examples from this is some from Sid's group, the personal robotics lab when used at CMU, but they're trying to use this like robot here to do motion planning to pick up these objects, often under obstacles and so on. And so they're trying to get it to a particular configuration, and they're going to like try and put obstacles in the middle, so that the robot has to maneuver around them and so on. And so what makes this problem difficult often is that certain objects can only be grasped in certain locations, and you have to like navigate through Flutter to do that. And so a lot of Sid's work kind of tries to do that. And it doesn't just have to be contact-free motion. Like you can also have the same type of planning methods to use for tasks like this. When you want to push this object here or do things with physics, you can also do planning. Right. The other challenge we haven't talked about so far is that in most industrial applications, right, you want to be able to do this in real time. Like if I want a robot to plan its motion, I don't want it to take 10 minutes to plan every motion, right? I want to do it quickly, and I want to do it in a way that's reactive. So for instance,
hello, my name is Yuan Shukan. I'm from the Direct Lab at Rice University.
Where they're trying to move this robot arm from left to right, so with motion, but they're going to stick an arm in the middle. Let's say you have a robot in a factory, you want it to go from left to right, or you want it to achieve some problem. But as soon as it detects a change in the environment, it should be able to swiftly replan how to do things safely without hitting it. And so they're going to have an example here where they stick an arm in the middle and it needs to quickly replan. So it has to do it in real time. So this is all operating at 1x. This is not sped up. You can see that the human might show up in the way, and your planner still needs to achieve what it needs to achieve, but needs to do so while avoiding. And so you can't use like a really, really expensive offline search because that doesn't work in real time. And so in factory settings, when you need to be super efficient, you want to use real-time planning. Right? I guess on a similar note, for problems like this, where you're, this is from the DARPA Grand Challenge, you're trying to like navigate around, or DARPA Urban Challenge, you're trying to navigate around some environment. You may not know the whole environment beforehand, right? It's like a maze. You don't know what the whole maze is. And so you need planning algorithms that are able to adapt on the fly, right? So let's say you have a best guess at your environment. You have to plan according to that. Then your environment changes. You need to be able to efficiently change your plan according to your new information. And so some of the methods you all will cover later this quarter will be methods for efficient replanning, right? And so in like these self-driving scenarios, when the map is not fully known, and like right now downstairs you map out the whole environment, but often in deployment you don't have that. And so we want methods that are efficient in replanning and able to do it in real time because your cars are moving fast, right? And so those are like some of the challenges that we would encounter in motion planning, things that are high dimensional, things that have lots of physical constraints, doing things in real time, doing things very gently, right? All right. So the other thing that you typically want in motion planning algorithms is you want a significant level of generality. So if I had to design a different planning algorithm for every robot, every setting, then it becomes like a very domain specific setting, right? So often the desiderata in motion planning algorithms is that you kind of want one algorithm that you can use for many different problems, right? So both across robot arm motion planning and across helicopter flight and across a car, you kind of want to have one algorithm. It's going to generate different plans. You might have slightly different hyperparameters, but you don't want a domain-specific algorithm for everything. So you don't want to have heuristics for everything. And so when we're trying to build these motion planning algorithms, one thing to keep in mind is that we want an algorithm that is easy to use for other problems, doesn't lead to huge drops in performance, and you can easily cast lots of different problems under that abstraction. And so if you all are ever building motion planning algorithms, try to build motion planning algorithms that work across multiple. The cons with doing that is like the cons with any like programming language too, right? You can have a very, very general programming language and it loses performance. Or you can have a DSL and that loses less performance. It's more specific. And so oftentimes we have these, the algorithm shown here, this algorithm called RRT, which is telling you it's very general, useful across lots of domains. And oftentimes what you do is you take RRT and then you make a bunch of domain specific adjustments. But the base algorithm is kind of the same. Okay. Any questions so far? So the setting we're trying to think about is we want some high degree of freedom system with physical constraints to go from place A to place B while obeying physical constraints and not hitting. But this sounds like control, right? What's the difference? This is exactly the same. We talked about trajectory optimization, graph dynamics, we want to minimize some costs, kind of the same thing. So we spent the last 3 weeks talking about control. Now I've thrown a new word at you and said it's different. Why is it different? Yeah.
No, this is like more like sort of like space and that's sort of possible actions, right?
Right. So often control is very local and planning is often more global. So they kind of solve the same problem or similar problems, but one of them is often more local and planning is often more global. So planning will often make discrete choices go left or right, whereas control is like, it's making choice on what actions to take, but very locally. And so the types of methods you use for control are typically gradient-based methods, things that are local search methods. Whereas the types of methods used for planning are more like discrete search algorithms or things that can like make combinatorial choices, right? So like going left or going right is not a choice you usually give to control. It's a choice you usually give to plan. But the problems are kind of similar. It's just a matter of like the level of abstraction you choose. And it's often the techniques we use for planning are techniques from search, and the techniques we use for control are techniques from optimization. Right? So just continuous versus discrete. Well, to be clear, planning is also a continuous problem, but you use more ideas from discrete things. And you do it at a level of making choices on where to go, whereas control is like at the very fine-grained level dealing with disturbances. Right, so like if you go back to the idea I mentioned at the start of the hierarchical abstraction, it's almost like you've hierarchically abstracted away the low-level path following to control and like deciding what the path is to. Okay, so to do motion planning, we need to kind of have a couple of different elements. The first is we need to specify and formulate the problem, right? We don't know what problem we're solving yet. The second is we need to understand if this problem is hard or not, or are we wasting our time? And the third is we need to start thinking about mathematical formalizations and abstractions that then solve the problem. Right. And so let's start by like formalizing the problem a little bit, and then we can go from there to the next two. Yeah. So specifying the problem requires us to have an abstraction that works across multiple different settings. So for instance, let's say you had 4 different problems, right? So you had a translating triangle, something like the piano movers problem, right? Translating and rotating triangle. You have a planar arm, so an arm which is in the 2D plane, which has to get around some obstacles. A race car, like you all have to, in this class. And you have a manipulator, so a 7-degree freedom arm, right? And we need some abstraction that captures all of these things, right? Because we kind of want to use one method across all of them. So to do that, we're going to introduce this idea of a configuration space, right? And so a configuration space or a C space, right, usually denoted by C here, it's a manifold which contains all the set of transformations that are achievable by a robot. Right, so we'll go in detail for each of these systems, but abstractly, what it means is that every point in the configuration space represents one configuration of the robot. Right? So a point in configuration space for an arm would be one configuration of the joint angles of point in the configuration space of your car is one position and orientation of it, right? And so every point in configuration space is corresponding to some configuration of the robot in the ring. Yeah, and it's a manifold because it's continuous. The manifold is something that is continuous and has a homeomorphism to Rn, right? So it's a continuous manifold that smooth. And it basically specifies the problem. It specifies, like you can specify every configuration of a robot by some point. Yes. And so what we've done now is we've like taken all of these robotics systems in the physical world, and we've said that any state of this system in the physical world can be mapped to a point in the configuration. And so like the state of an arm can be represented as a vector, the state of a car can be represented as a vector, the state of the piano can be represented as a vector, right? In some higher dimensional space. So let's try and make this a little more concrete. So let's start with a translating triangle, right? Moves in X and Y. And so the configuration space in a translating triangle is X and Y, right? So it's a two-dimensional configuration space. So essentially the robot, every position on every point on the robot is completely defined by one X and Y position, right? Basically, like because it's a rigid body, every point of this robot can be completely determined by one X and Y position, right? So you can summarize a configuration of the system by an X and a Y. So you have a two-dimensional Cartesian space between R and R, and that's going to be a configuration space, right? Super easy. Let's go to a slightly more complicated thing. You have a two-dimensional arm. What is your configuration space? So two-dimensional arm fixed in the plane. It just moves. It moves the first joint and moves the second joint. Now you want to define a configuration space for this. So like you want to be able to define any configuration of this. So what are the configuration space?
So just like
Theta 1 and theta 2. That's it. Right. So you're going to have this. You denote it as S1, but essentially S1 are just angles, right? So you have angle 1 and angle 2. So your configuration space is going to be theta 1 and theta 2. And so you can graphically represent this as like torus. So basically, theta 1 is an angle here, theta 2 is an angle here. Okay? But it's just like an easy way, or you can also visualize that on the plane if you want. But the only difference between these and the translation is that theta wraps around. Right? It's an angle, so like once it goes to 360, it wraps around. And that's why it's easier to represent it here rather than a flat plane, because it's not that it keeps going. In here, the configuration space wraps up, right? That's why you want to represent it. Does that make sense? So a 2D planar arm is fully specified by theta 1 and theta 2. And then every other point on your system can be fully determined by its values of theta 1 and theta 2. So June was talking to me a little while ago about June, I got you. Yeah, okay. He's talking to me about inverse kinematics, right? And so if you've heard about inverse kinematics, inverse kinematics basically says, given a point of the robot, given an end effector point of the robot, what is theta 1 and theta 2? And for kinematics says, given the theta 1 and theta 2, where is the point of the robot? Right? And so because it's a rigid body and it's fully defined by theta 1 and theta 2, you can think of forward kinematics as something that connects theta 1 and theta 2 to points in the 3D space or the 2D space. And inverse kinematics that connects points on the 2D space back to configuration space. So if you ever see those words in any papers, that's kind of what they refer to. Cool. So that is a 2D arm. Everyone with me so far? Okay. Now, the problem that we really care about is this race car, right? So in the race car, your configuration space is the X, and the Y, the theta, right? So it's R2, which is because you have X and Y, and then you have S1 because you have theta, which is your heading, right? And this is a group that you're going to call SE2, special utility group, right? And so it's saying that you have 2 degrees of freedom for translation and 1 degree of freedom for rotation. And to keep going with this, you can kind of define configuration spaces for lots of different systems. So we've talked about a mobile robot translating in the plane. We talked about a mobile robot translating and rotating in the plane. But you can also have, something like a spacecraft, and the spacecraft is not restricted to the plane. You can go any orientation, any position, right? And so you have something in SE3. By SE3, you mean you can do X, Y, Z, and then theta 1, theta 2, theta 3. Right? If you have an n-joint arm, the configuration space is like n-dimensional theta 1, theta 2, theta 3, theta 10. And when you have something like a mobile manipulator, like an arm on a mobile base, then you're going to have 3 degrees of freedom for motion of the base. So you're going to have SE2, which is saying you can translate in X, translate in Y, and rotate. And you're going to have n degrees of freedom for the arm. And so whenever you define a robotic system, you want to define its configuration space, because that tells you, what's the minimum statistic to describe the robot at any point of time. This kind of like defining the state space and all the problems we've defined so far. It's kind of like defining the state. But we'll talk about why it's a little more complicated than that. So far, everyone with me? Okay. The tricky part is when you have obstacles, right? Obstacles don't live in configuration space. Obstacles are in the world, right? So configuration space is a manifold that describes, like, basically I can say I have an arm. The arm is at, theta 1, theta 2, right? But obstacles don't live in this like theta 1, theta 2 world, right? Obstacles live in like the Euclidean, the real world, right? And so when I want to do planning, I need to either bring the obstacles to the arm space or the other way around, right? And so let's think about why that becomes tricky. So obstacles are going to live in this thing called the workspace or the world space, right? It's like the Euclidean 3D space or the Euclidean 2D space, right? Obstacles live in that space. So that's going to be called your workspace. Some subset of that space is going to be obstacles, right? So it's like, imagine this was your world, like these are going to be your obstacle space. Right? So usually in most motion planning problems, you're going to know what your obstacles are going to be. Some of them you'll discover them on the fly, but you'll know what your obstacles are going to be. And there are going to be some regions of your workspace which you cannot collide with, right? Which means when I say cannot collide with, I mean no portion of your robot can collide. Yeah. And then you have this thing called your geometric shape of your robot. So your configuration space is not the same as your geometric shape of your robot. Your configuration space is a 2D number for, let's say, a planar arm. It's going to be theta 1 and theta 2, right? But the geometry of the robot is basically a mapping from theta 1, theta 2 to like all of the points that like the robot occupies at any point, right? And so this AQ function, right, for notation wise is saying, given some Q configuration space, you're going to map into the set of points or the submanifold that the robot is going to occupy at any point. So it's saying, let's do this on the board. So basically it's saying that, let's say you have a robot arm, right, with theta 1, theta 2. The configuration space at that point is going to be theta 1, theta 2, right? And then what you're going to do is for any theta 1, theta 2, it's going to give you some part of the workspace that your robot occupies at that point of time. And that's important because no part of your robot can touch an obstacle, right? And so this thing lives in configuration space, like in R2, right? And you're going to have some ASQ, which is going to be all of the points in world space. Right? And so what you really want to do is you want to find a path through this configuration space. You want to find a series of configurations of your arm so that it does not collide with any obstacles. And that means that no point inside AQ collides with any obstacles. Does that make sense? So when you have an obstacle, it's going to be defined in world space, right? But then you need to do planning. You need to plan how to get through configuration space. Like the robot doesn't live in world space, it lives in configuration space, right? You can only control your robot through changing its configurations, right? You can't like tell the robot where to go magically. You can only change the motor degrees in your arm. So what you need to do is you need to figure out, how do I take an obstacle? Let's say I have an obstacle here, right? And how do I map it into configuration space? So that the mapping of the obstacle into configuration space represents all points where something in the body is in contact with the obstacle, right? So it's saying, let's like kind of look through this definition here. It's saying that an obstacle mapped into configuration space is the set of all configurations where the intersection between the body of the robot at that cube and the obstacle is non-zero, right? So it's all configurations where the robot body is intersecting with an obstacle, right? So it's important to remember this, right? It's the robot lives in configuration space. The obstacle lives in world space and workspace, right? And what you need to do is you need to map the obstacle into configuration space to do that. And so essentially what you're trying to say is try to find all the points in configuration space where the body of the robot is intersecting with an obstacle. And that is the obstacle mapped into configuration space. Does that make sense intuitively? We'll go through some examples to make this concrete. But at a high level, it's saying, try to find all configurations where something is in contact, and that is the representation of the obstacle in configuration space. So let's try to ground this in a concrete example. I know this is a little confusing. Let's ground it in a concrete example. So we have this robot, right? We have this robot which is denoted, its configuration space is X and Y. It's a translating triangle. Yeah. And its body is denoted by this A and Q, which is like the body of this triangle, right? So given some X and Y, you can always compute A and Q. You know the shape of the body, you know its orientation with respect to X and Y. And your obstacle in the world space is this rectangle. Yeah. And what you're trying to do is you're trying to figure out what is the obstacle going to look like in configuration space. Right. So the configuration of the robot is going to be an X and a Y. Right. So let's put this in for a second. The configuration of the robot is going to be an X and a Y. And you are trying to figure out for what set of X's and Y's is the robot in collision with the obstacle, right? So you're trying to find out, like, can I define a surface such that inside the surface, every point has the robot in collision with the obstacle, right? So let's try to see what it looks like here. The obstacle in configuration space looks something like this. And we will work out why exactly that is. Here's an intuitive way of thinking about it, right? So imagine that let's try it right on the board. So imagine that you had your obstacle in world space like this, yeah? And you're trying to find, and you have your triangle like this, and this is your current X, Y position. Right? You're trying to find all of the points, right, where the robot is in intersection with some point in the obstacle, right? So you know that over here, this point has to be in collision space because over here, this point is colliding, right? Does that make sense? So this is the obstacle. This is the robot. Yeah. So when the robot is at this X, Y, this point is colliding with the obstacle. Hence, this point has to belong to configuration space, right? Or this point has to belong to a configuration space obstacle. So you can kind of think of it that way. And similarly, when you move the robot over, it's here, right? Again, a point is colliding with the obstacle. So this point has to belong in the configuration space, right? And now when you bring the robot down here, you can see this point is colliding, right? And so this point has to lie in the configuration space obstacle, right? And so if you like, essentially you can think about it like translating this triangle all around and then trying to see for what X, Y's does this thing collide with this thing, right? And when you like draw that out, it gives you a surface that looks like that. So here's a sanity check. Put the X, Y at the top right corner of the triangle at any point inside this whole space and the triangle will be in collision with the square. Okay, and so what that means is that in the configuration space of the robot, if the robot is at any of these points, it will be in collision with the obstacle. Does that make sense? But it's not like you literally took this. The important thing is not like the obstacle, which was a square in the world space, is a square in the configuration space. Right? So like the transformation of seemingly simple obstacles in world space into configuration space gets kind of nasty. Okay, so does this simple example make sense? Everyone with me? Yes. Any questions? It's not a super trivial concept. It's going to be important. So ask me any questions here. Yeah.
They're like places to pump right corner of like top left corner of the black area. In the diagram.
Oh, you mean this point right here?
Yeah.
Yeah, I think this one should be down here. I think this one should be down here. Yeah, good question. So yeah, you're right. Like basically, the sanity check, you put the triangle over there, it doesn't actually intersect with anything. So like that thing should actually be down here. Okay, good catch. Okay, so now let's go to a slightly more complicated system. This is a translating triangle. Let's think about a translating and rotating triangle, right? And one way to construct the configuration, in that case, the configuration space is three-dimensional. You have X and Y theta, right? So we have X, Y, theta. And one way to construct the configuration space is that you divide it into different slices, and each slice corresponds to a different theta, right? So try to think of like, imagine you froze the triangle to some rotation and then just translate it around. That gives you one slice that looks like this thing from the last slide, right? And then you do like many different slices on top. Right, so you can think of you can think of a triangle that is rotating and translating as a combination of many just translating triangles, right? So like slice up this space into a fixed theta, find out what the configuration space obstacle looks like for fixed theta with the thing we just did in the last slide, right? And then it's going to look different for every different orientation, right? So imagine that you like, imagine that your triangle now was, instead of facing this way, it was facing this way, right? Your configuration space now looks different, right? And so you can see that this configuration space obstacle here is essentially like a stack of a bunch of configuration spaces for different orientations. And so you can see that it's like a really simple obstacle in world space looks like this nasty kind of obstacle in configuration space, right? Does that kind of make sense? Intuiting? You can kind of do the same thing for, you know, like a rectangle. It kind of looks like that. And like a more nasty looking obstacle, you'd see like you get some of the weird 3D shapes. It's often like pretty counterintuitive to do this, and you often won't actually do this explicitly, but it's more for visualization. But part of what makes motion planning so hard is that mapping configuration and world space together is like this non-trivial exercise. And so let's take a look at some examples from different arms, right? So you have like a two-link planar arm, and you have a bunch of these different obstacles. But do I have a different one? Sorry. Yeah, so the different obstacles here are colors in different colors, right? And you have the theta 1 and theta 2 on the axes. And you can see the obstacles mapped into configuration space give you this like real nasty obstacle space, right? That you have to plan through. That makes sense? Even with a two-link arm with one really simple obstacle, it looks kind of like that, right? And so some points are not even reachable through the obstacle space. So that's kind of like an intuition for what makes the problem hard. So let's try and define our problem a little more clearly. A motion planning problem, something where you have a workspace W, an obstacle region O, which is a subset of W, some subset of your space is an obstacle. You have a robot that is defined by some set of links, and you have a configuration space for the robot. Configuration space defines how your robot is configured at any point in time. You have an initial configuration, which is in free space. You have a goal configuration, which is in free space, right? So you don't want to go to something that's in collision, that's like a poorly defined configuration. So you have free space start and a free space goal. And what you want to find is a continuous path that takes you from the start to the goal and does not collide with anything in the process, right? So you want to find, in continuous space, you want to find a curve, but oftentimes you will find a series of poses, right? A discretization of the continuous path, something that takes you from the initial pose in configuration space to the final pose in configuration space. And then you stick that into a control algorithm, and then it follows the path, and then you have what you need. Does that make sense as a problem definition? Any questions? Does it seem crazy in any way? Not so far? Okay. So,
Some more complicated example.
let's see, we have 2 minutes. I'm gonna skip this. Here's an example I found kind of compelling. It's like, this is your planning problem here. You have this triangle in all of these these different like obstacles, and the configuration space looks like that. And so that's showing how planning works in the configuration space. You have to like navigate through this nasty, non-convex, like difficult space, which is even hard to characterize. Right, and so planning is non-trivial because of like how you map these obstacles into non-continuous situations. And so you can see that like to navigate through that space, you have to like do some pretty non-trivial motions. And so oftentimes you'll see like motion that arises like this, like for instance, to get back into that corner, you have to do like real interesting motion planning like that. Okay, so we formalize the problem. Let's try and understand the problem difficulty a little bit, right? So if you had 2D planning, like just translations, and you had polygon obstacles, right? Then motion planning can be solved with this thing called visibility graphs. You basically have construct a graph where all the nodes correspond to edges of like corners of the polygon, construct a graph, run graph solution. Will work for 2D navigation with polygon obstacles. But for any more complex problem, it doesn't work, right? And so one of my professors from undergrad, John Canny, he actually showed that even the simple piano movers problem, which is just translation and rotation, is P space hard. P space is bigger than NP, right? And if you have 3D robot planning, then it's next plan hard. So P space means that you have memory, which is polynomial, right? And next time is like solvable with an exponential Turing machine, something bad, right? So in general, we're not going to solve motion planning problems efficiently. And so what we're going to try and do in the next 3 lectures is come up with good approximations that are guaranteed to do reasonably. Okay. So generally, a geometric path planning problem is kind of a combination of a workspace, obstacle region, configuration space, start and goal configurations, and you try to get a collision-free path, right? And so what we're going to figure out over the next 3 lectures is how we can do this efficiently while not being too bad, right? Okay, I think we're out of time for today, but see you all Monday.